All right, let's just dive right into this. We spend so much of our time building apps, designing these beautiful interfaces, and writing code. But how often do we actually stop to think about the invisible machinery running underneath every single app we use? Today, we're going to deconstruct exactly what happens when your database saves data. We're talking about the hidden engine room of systems like Postgres, MySQL, MongoDB, and SQLite.
It's a really simple question, right? But honestly, almost no tutorial ever actually answers it. You write a command like insert into users, you hit enter, and what then? Magic? Well, not exactly. Today, we are fully pulling back the curtain to reveal the incredible engineering magic happening right under the hood. We're going to explore the exact concepts that guarantee your data isn't lost, the tricks that let you search billions of rows in milliseconds, and really just what makes modern data storage possible.
To make sense of this whole journey, we're going to look at 4 specific tools: Pages, B-Trees, LSM-Trees, and the write-ahead log. And then we'll put the whole engine back together. Okay, so first up, Pages, or what I like to call the warehouse shelves. So, fun fact, databases don't actually think in terms of single rows of data like we do. It's all about sizing. Disks, especially older hard drives, but honestly, even modern SSDs, are terribly inefficient at moving tiny little bits of data one at a time. If a database had to spin up the disk to fetch just a 50-byte user record, your application would literally grind to a halt. So to get around this, every major database groups your data into these fixed-size blocks called pages. They're usually somewhere between 4 and 16 kilobytes. And the catch is, even if you only want a single row, the database is going to read the entire page that your row lives on right into its memory. Just think of it like a massive warehouse. Driving a forklift all the way down an aisle, grabbing one tiny box, driving all the way back, and then repeating that for every single item you need, that would be excruciatingly slow. So instead, the forklift just brings you the whole shelf. In database terms, it brings the whole page and drops it into an in-memory cache called a buffer pool. Actually, this one single design decision explains why adding just a tiny column to a table can sometimes slow everything down, because fewer rows fit on a single page, which means way more trips for the forklift. All right, that brings us to part 2, B-trees, basically the airport signs of your database. So if our data is grouped onto thousands or even millions of different shelves, how do we find the exact row we want without scanning the entire warehouse? Imagine you've got a massive table containing 1 billion rows of data. If you don't have an index, the database has to perform what's known as a full table scan. It literally has to check every single row, one by one, just to see if it matches your query. With a billion rows, you might be waiting seconds or even minutes for a result. And let's be real, we need answers in milliseconds. To fix this, the database uses an index, and the most common type out there is a B-tree. A B-tree is this beautifully balanced, wide-branching data structure. And because it's so wide and shallow, it actually allows the database to locate your exact row among a billion rows by checking only 3 to 4 pages from the root of the tree down to the leaf. It is an incredibly efficient way to navigate data. If you've ever navigated an airport, you already know exactly how a B-tree works. You don't walk past every single gate looking for gate C42, right? You walk in, and the first sign points you towards concourse C. You follow that, and the next sign points you down a hallway for gate C40 through C50. And then the final sign points you directly to gate C42. Just 3 signs, and you found it among hundreds of gates. By using these simple descending comparisons, a B-tree index instantly jumps to the right page. It completely transforms a sluggish 10-second full table scan into a lightning-fast 1 millisecond query. Now let's look at part 3, LSM-Trees, which are the modern alternative. But what if your app is logging data so ridiculously fast that constantly updating those B-trees on the disk just becomes a massive bottleneck? Well, that's exactly where the log-structured merge tree, or LSM-tree, comes in. See, while B-trees are the absolute gold standard for read-heavy systems like Postgres or MySQL, LSM-trees are custom-built for write-heavy workloads. Instead of constantly doing these slow, in-place updates directly on a disk, an LSM-tree appends new data to memory first. It just quickly writes it down sequentially. Later on, a background process flushes that memory to disk as immutable files. It trades a slightly slower read time, because it might have to check a few different files, for dramatically faster writes. That's exactly why tools like Cassandra and RocksDB rely on them for massive, high-speed data pipelines. Which brings us to part 4, the write-ahead log. So updating these main data files on a disk is usually done in memory first, right? Because it's way faster. But that introduces this terrifying scenario. You've just told the user their data was saved, It's sitting there in the fast in-memory buffer pool, waiting to be efficiently written to the actual disk pages later. And then, bam, the power gets cut, the server crashes, memory is totally wiped clean. If the system crashes before that memory is flushed to disk, your data could be corrupted or just lost entirely. It's a total nightmare scenario. But databases don't actually lose data when the power goes out. Why? Well, this is where our next tool totally saves the day. Thankfully, almost every reliable database out there guarantees you won't lose data, and they do it using a write-ahead log, or WAL for short. Before the database even touches the actual data pages in memory, it does a very fast sequential write to this log on the actual disk. It simply writes down, hey, I am about to insert this exact record. Only after this log entry is safely written to the physical disk does the database consider your write durable and confirm success back to your app. Think of a super busy restaurant kitchen. The write-ahead log is like a chef quickly writing a new order on a ticket and immediately clipping it to the rail before they even think about chopping vegetables or cooking the meat. Clipping the ticket is super fast. Cooking takes a lot of time. Even if the chef gets pulled away mid-dish by a power outage or a fire alarm, it's completely fine. When they come back, anyone can just look at the ticket rail upon restart, know exactly what was ordered, and replay the work safely. The database does the exact same thing when it boots back up after a crash. It just reads the WAL to reconstruct absolutely anything that was lost from memory.
Okay, part 5. Let's get the engine reassembled.
We've got all our puzzle pieces now, the warehouse shelves, the airport signs, and the kitchen ticket. Let's watch the whole machine run together in real time. Step 1. Your application sends the insert command. Step 2. The database safely writes this intended change to the write-ahead log on the disk for durability. Step 3. Having secured the log, it immediately tells your app, success, I've got it. Step 4. The actual data page is updated in the fast in-memory buffer pool. Step 5. The corresponding B-tree or LSM-Tree indexes are updated in memory so the data can actually be found later. And finally, Step 6. At some point in the future, a background process quietly flushes these modified, dirty pages from memory to the actual disk for permanent storage. That's the complete loop. It is just wild to think that all of that orchestrated complexity happens in literally a few milliseconds right after you hit enter. Now that you know exactly how databases organize, index, and protect your information under the hood, you really have to wonder, what other fascinating secrets are hiding inside the tools you rely on every single day? How does a load balancer actually distribute traffic? How does a cache truly decide what to forget? Well, those are exactly the kinds of questions we are going to explore in the next explainer. Thanks so much for joining me on this deep dive into database internals, and I'll catch you next time.